Hi guys, so you just read the Google post and you know that I'm in a workshop today from 12:15 to 2:30 for ESL, so I will not be in class today. So your job is to watch this video lesson and complete the notes Unit 3 Day 4 that are attached to our Google post here. That's your classwork number 3 assignment. You're going to upload those 100% completed and accurate by the end of the block. Your homework tonight is homework number 5. It's a quiz review for 2 points. You're going to upload it to the assignment by next block, and that's a review of everything on our polynomials quiz that's going to be on December 10th. So not next block, the following block we'll be having a quiz. I mentioned it last block. It includes everything from day 1 through day 3A notes, includes the homework number 1 through 5 that you're completing tonight, and all the classwork. All right, and to remind you, the test is on December 18th. So what we're going to be doing today is learning how to divide polynomials with a little easier method called synthetic division, and we're also going to learn about what the remainder theorem is. So our objectives here, as I have listed, are dividing polynomials using synthetic division. We're going to identify linear factors of polynomials using synthetic division, and we're going to graph and analyze polynomials using their factored form. So you're going to pause the video and you're going to do now number 1 and 2 and see if you can find a pattern between the long division and evaluating this function for a certain value of x. So here, the first one you're going to evaluate when x is 8, plug and chug. The second one you're going to plug in -1, and you're going to see a pattern, and I want you to come to a conclusion. So pause the video now and complete 1 and 2. Okay, so for number 1, you should have gotten 2x minus 3 using our long division from the past 2 blocks, and the remainder was 0. When I asked you to plug in 8 for x and evaluate the function when x is 8, you also got 0. Coincidence or not? So now we try number 2, and you should have gotten x squared plus 3x minus 2, and then you got a remainder of -4 over x plus 1. And then when I asked you to plug in -1 and evaluate the function, you should have gotten -4. So you're starting to see a pattern there. When we evaluate the function, that function value is a point, right? 8, 0 for the first one, and -1, -4 for the second one. So when we do this division, what we're finding when we find the remainder is the actual y value of the function. So here for number 1, if I go to graph that at x equals 8, I have a 0 in my function. The y value is 0. But when I do number 2 and go to -1 to graph it, I'm way down here at -4, and that has a remainder because it's not a good 0. All right, so what you found is a connection between division, the remainder for the division, and evaluating the function, the y value of the function. They're the same thing. So let's go to the conclusion box, and the pattern we notice is that when you evaluate that function, you'll find out if it's a good 0 or not. If you get 0, then it's a linear factor and a good 0 of your function. If it's any other number, it's not. Okay, so our conclusion for the remainder theorem is if a polynomial, any polynomial p of x, of degree 1 or higher, so linear and higher, when you divide it by x minus a linear factor, so when you divide it by a linear factor in the form x minus some number where a is a constant, then the remainder is going to be p of a when you plug it in. So when we divided by x minus 8, we got a remainder of 0, which is the same as if we had plugged in the 8. They were both 0. When we did -1 or x plus 1, and it has to be after a minus sign, so the a was -1, and we plug that in, there we got a remainder of -4. So anytime you're looking for a linear factor, a quick check will be plug in that a value after the minus sign. So do the opposite of what you see in the factor. If it's x minus 8, test +8. If it's x plus 1, test -1. Whatever you get there is going to be your remainder of the function. So if the remainder of that function is equal to 0, what we just found out and what we knew from long division is we know that x minus a will be a linear factor. So it's a good factor and we can use it to divide to get to a quadratic to split up our polynomial. So we're going to use this remainder theorem this year as a quick way to check, is a factor a good factor of a polynomial? We don't want to waste our time and do all the division if it's not. So here on the examples, we're going to use this remainder theorem to determine whether these three expressions, x minus 2, x plus 3, and x minus 3, are good factors of this quartic polynomial p of x. So it's pretty long. We don't want to have to do the division, so we're going to do a quick check to see if they're good zeros or not. So if we end up with 0 as our remainder, then we know it's a good linear factor. So remember, it's always the opposite of a. So it's after a minus sign. So here, if you're testing x minus 2, you're going to plug in positive 2, the a value. If you get 0, it's a good factor. If not, any other number but 0, it's not. For the second one, you're going to be testing negative 3, because that would be minus a negative 3. And for the third one, you're going to test positive 3. So I want you to pause the video now and plug those into the polynomial function p of x and tell me what the remainder is. Okay, so when you plug those in for a, when we tested the a value of 2, you end up with 0 as your remainder. So the remainder theorem tells us when we evaluate that function at x equals 2, we got y is 0. It's a good 0, so we're going to say yes, and you would divide by it to get to a cubic equation. Now we're going to test negative 3. So x plus 3, the a value would be negative 3. You should have also gotten a 0 there, which means the point negative 3, 0 lies on that function. It's a good 0, so we're going to say yes. For letter C, x minus 3, we have to test positive 3, and you end up with 216. So that is definitely not a 0. That would be way up in the first quadrant at 3, 216. So that would not be a good 0 or linear factor. Okay, so this is a quick check, a way for you to tell if a factor is a good factor and should we divide by it. Okay, so we're going to be using this remainder theorem along with this synthetic division today to find good factors of this polynomial. Okay, so synthetic division, again, has the same purpose as long division, but you simplify the process by omitting all the variables and exponents. So I think you're going to like this today. So here is one important note, the most critical note today. You can only use synthetic division for linear factors. Oops. So it only works in the form of x minus a, linear factors of degree 1. Okay, so first we're going to take a look at when it's an x minus a form, a linear factor. We're going to learn to divide with synthetic division. What you did in the do now is long division. So the first example is going to be what you did in do now number 1, but this time I'm going to use synthetic division. So when you use synthetic division, the first thing you do is you take the a value out of the factor. So here x minus 8, 8 is our a value. And we're going to divide by that value. Now, it's always going to be the opposite of what you see in the factor. So it's negative 8, so we're dividing by 8. And then instead of listing this entire quadratic function, we're just going to take the coefficients of each term. So I'm going to take the 2 from the x squared, I'm going to take the negative 19 from the x, and I'm going to take the 24 as the constant. Now what you're going to do is set it up. What you divide by goes in this little bracket here, and you're going to put some division bar. And then what you're going to do is bring down the first value. So you always bring down that leading coefficient. And then it's going to be a pattern of multiply, add, until you hit your remainder, your last column. So here we're going to multiply our a value, 8, by 2, and we get 16. We're going to put it in the next column, and then we're going to add down. We're going to get negative 3. We're going to multiply again. 8 times negative 3, we get negative 24. Add down, and we find that we get a remainder of 0. Now, I want you to look back at your do now with all those x's and x squareds in it, And what do you notice about the 2 and -3? Well, what we have here is a linear term. We took a degree 2, we divided by a degree 1, so we end up with 2x minus 3, the exact same thing you got with long division, writing a heck of a lot more, right? And that's the procedure for synthetic division. So let's try example 2, which is from your do now number 2. So here I'm dividing the cubic expression by a linear factor x plus 1. So my a value is going to be the opposite, or -1. So if you don't see it, all you have to do is set that equal to 0, and you'll find what your a value is. All right, so we're going to divide by -1. I'm going to put that in a little division bracket. I'm going to make sure my polynomial's in standard form, no missing terms for placeholders. And I'm going to take all those coefficients and list them. So I'm going to have a 1x cubed, a 4x squared, a 1x, and a -6 for my constant. I'll put my bar down, and then I'm ready to go with the multiply add pattern. So I'm going to bring down the 1. I'm going to multiply the a value times that 1. I get -1. Add down, you get 3. Do it again, -1 times 3, we get -3. We're going to add down and get -2. We're going to multiply again, -1 times -2 is +2. And what do you know? We got the same remainder as you did with long division. So take a look back at your do now number 2. And here we did a lot less writing, and we have our quadratic quotient. So here I divided a cubic degree 3 polynomial by a degree 1. So this should be 1x squared plus 3x minus 2, except this time I have the remainder of -4 over x plus 1. So all I did was divide. Same procedure as long division. You just take away all of our variables, exponents, the things that gets everyone confused, and it's basic numbers. All right, so I'm going to try example 3 now, and I want you to take a look at that. It's a little different than these two. All right, so remember, when you have missing terms, you're still going to use those zeros as placeholders with synthetic division, just like you did with long division. So we have a little problem here in example 3 where I'm missing the x squared term. So I'm just going to add in a plus 0x squared so I don't forget that placeholder. Everything's in standard form. I'm ready to go. Now again, with synthetic division, I have x plus 4. It's a good linear factor. I'm going to take the opposite, and my a value I'm going to be dividing by is the opposite of +4, or -4. So I'm going to set that up. And now I'm going to put all my coefficients of that cubic polynomial. So I have 1x cubed. I have 0x squared, my placeholder. I have -13x's, and I have 12 as my constant. I'm going to put my bar down, and you always bring down that leading coefficient of 1 here. Then you're going to take the a value and do that multiply add pattern. So -4 times 1 is -4. Going to put it in the next column, add down. I get -4. You're going to multiply again. -4 times -4 is +16. I'm going to add down, and I'm going to get +3. And then -4 times 3 is -12. Add down, and this time I get a remainder of 0. So I have a good linear factor, and I can take that x plus 4, and I now know that the quotient and what I can multiply it by, I had a degree 3. I took away 1 degree, so I have 1x squared minus 4x plus 3, and that cubic polynomial expression is now split into 2 terms. And then what I can do with my quadratic, it's old stuff, right? We can split that up into x minus 3 and x minus 1. And now I have all 3 factors of this polynomial expression. And you're done. Okay, so now we're going to take a look at, we know not all linear factors look like this, right? They're not all nice and neat, x plus 4, x minus 3. Sometimes we have other factors like 5x minus 1, 2x minus 3. What do we do when we have that a value out front, a leading coefficient out front? That's what we're going to talk about next. Okay, so in example 4, we have 2x plus 7 as our linear factor that we're dividing by. Now that is not in the form x minus a, so we're going to make sure we put it in that form. So what you're going to do is distribute out the 2 so that you get the x minus a. So when we divide everything by 2 here to take it out to the front, we end up with x plus 3.5 in the parenthesis. Now keep a note. We are multiplying by 2 in the beginning, so at the end we have to divide by 2 to balance back that expression. So here, since we're multiplying by a factor of 2 with the x minus a, you must divide by 2 to balance back the expression, and I'll show you why once we divide. Okay, so we're going to use synthetic division. So again, here you have to take that a into account. So it's the opposite of the 7 divided by 2. If you don't see that, set it equal to 0. We're still dividing by that a value or that 0. So we're going to subtract the 7 over, divide by 2, and we get that negative 3.5. Okay, so it's always the opposite of that a value once it's in x minus a format. So we're dividing by negative 3.5. And now I'm going to list all the coefficients of my polynomial. I'm going to make sure it's in standard form, and I need no placeholders. So here I go 3, 2, 1, negative 42, so I'm good. So I'm going to list all my coefficients. I have a 2x cubed, a 17x squared, a 23x, and a negative 42. I'm going to put my bar down, and we're going to follow our pattern. You're always going to bring down your leading coefficient. Here it's 2. And then we're going to multiply, add, multiply, add. So negative 3.5 times 2 is negative 7. I'm going to add down, you get 10. Negative 3.5 times 10, I get negative 35. And I'm going to add down, and I'm going to get negative 12. And then negative 3.5 times negative 12. Okay, so negative 3.5 times negative 12 is positive 42. And add down, and you get a remainder of 0. Now, it's a good factor, a good linear factor, but if I go back and put in my variables, what I end up with, I started with degree 3, I took out degree 1, so I end up with 2x squared plus 10x minus 12. And if I put back my 2x plus 7, you can see this is not going to work. I end up with 4x squared, and 4x cubed, and I need 2x cubed. So remember, we multiplied by this 2 in the beginning, so at the end, you're going to have to balance it back and divide by 2, and our polynomial split will be 2x plus 7 times x squared plus 5x minus 6. All right, and we have our factors there, and then what we can do, if we need to go further to factor completely, we'll take that quadratic and do two numbers that multiply to negative 6 and add to positive 5, are x plus 6 and x minus 1. So now we have a complete factorization of that polynomial. All right, now what I want you to do is try the next problem, 8x to the 4th. So you have a quartic polynomial being divided by 2x plus 1. Make sure you take that 2 into account, do your division, but remember to divide by 2 at the end. Okay, so how'd we do with this one? First, we found out that we have a coefficient in front, so I had to distribute out and take out that 2, and now I have a linear factor in the form x minus a, and my a value is negative 1/2, but I have to remember that I'm multiplying by 2, so when I divide, I then have to divide that polynomial that I get, that quotient, by 2. So here I did the division over here. Be very careful, we needed a 0x cubed placeholder. And when you divide this time, you end up with a cubic polynomial. Okay, so here I started with degree 4. I divided by an x to the 1. I took away an x. So I end up with 8x cubed minus 4x squared minus 2x plus 2. plus I have a remainder of 3, and I'm going to put that over the 2x plus 1. But remember, I multiplied by 2 in the beginning, so I'm going to have to divide this by 2. Now, you never divide the remainder because we put that 2 back in the denominator when I put the 2 back in my factor. So here I'm going to end up with 4x cubed minus 2x squared minus x plus 1, and then I have that remainder 3, which I'm going to put over my 2x plus 1, so I divided that remainder. And now that is my quotient when I divide it by 2x plus 1. Okay, so here not always are we going to get a linear factor that's going to work. If you get a remainder, you're going to leave it and try something else. Okay, so you're going to try some class practice. Obviously, we're not in class to partner up, but you're going to try number 1. Oops. So number 1 and 2, you're going to divide using both long division and synthetic division. And you're going to tell me, is it a linear factor, yes or no? And if it is, factor the expression completely. Then in number 3, 4, and 5, you're going to divide using just synthetic division. Tell me, is it a linear factor or not? If yes, factor it completely. And then for number 6, you're going to use our old skills plus division, and you're going to graph this polynomial function. It's a cubic function. You're going to make a quick sketch of it, finding all the zeros, finding the end behaviors, finding the y-intercept, and getting a quick sketch. All right, and then for number 7, there's an application problem there, similar to one we did in homework number 4, where I'm giving you a rectangular tank, and I give you the depth of the tank, and you're going to find the length and width of the tank. All right, so that is your classwork. You're going to upload these. I'm going to take a look at your effort. And if you do number 1 and 2 by long division, you already know the answer, and that should match your synthetic division. All right, and you're going to turn this in by the end of the block today, and then you have homework number 5, which is your quiz review. So have a great weekend, and I will see you guys on Tuesday.